Hello and welcome to my walkthrough of Philipp Oppermann's Rust OS. The link to this is in the description. The previous videos have gone through the whole bare bones section, which is the freestanding Rust library, minimal Rust kernel, VGA text mode, testing. We walked through the CPU exceptions, double faults, hardware interrupts. And now we're on the memory management section and we're in allocator designs. The previous videos were two of the designs in the allocator designs, the bump allocator and the linked list allocator, and now we're on the fixed block allocator. So let's dive right in. Let's just make sure this all still works, right? Oh, we ran the test right here. We committed and then we pushed, so I think we're okay. Yep. In the following, we present an allocator design that uses fixed-size memory blocks for fulfilling allocation requests. This way, the allocator often returns blocks that are larger than needed for allocations, which results in wasted memory due to internal fragmentation. On the other hand, it drastically reduces the time required to find a suitable block compared to the linked list allocator, resulting in much better allocation performance. Yeah. Okay, wasted memory due to internal fragmentation. Okay, I guess we'll learn about how that all gets put together. The idea behind a fixed size block allocator is the following. Instead of allocating exactly as much memory as requested, we define a small number of block sizes and round up each allocation to the next block size. For example, with block sizes of 16, 64, and 512 bytes, an allocation of 4 bytes would return a 16-byte block, an allocation of 48 bytes, a 64-byte block, and an allocation of 128 bytes, a 512-byte block. Like the list linked allocator, we keep track of the unused memory by creating a linked list in the unused memory. However, instead of using a single list with different block sizes, we create a separate list for each size class. Each list then only stores blocks of a single size. For example, with block sizes 16, 64, and 512, there would be 3 separate linked lists in memory. Yeah, that makes sense. One of the things that would be able to reduce fragmentation using this scheme is to, instead of doing single 16-byte things, is just allocate a chunk of them all at once. They're all 16 bytes to contiguously, and then hand those out individually. Right, and that way when they get freed, they're automatically freed back into the 16-byte region, and they can automatically, well, they can easily coalesce together. But maybe we'll get into that. Instead of a single head pointer, we have 3 head pointers, head 16, head 64, and head 512, that each point to the first unused block of the corresponding size. All nodes in a single list have the same size. For example, a list started by head 16 pointer only contains 16-byte blocks. This means we no longer need to store the size in each list node, since it's already specified by the name of the head pointer. Yeah, that makes sense. Since each element in a list has the same size, each list element is equally suitable for an allocation request. This means we can very efficiently perform an allocation using the following steps. Round up the requested allocation size to the next block size. For example, when the allocation of 12 bytes is requested, we would choose the block size 16 in the above example. Retrieve the head pointer from the list, e.g. from an array. For block 16, we need to use head 16. Remove the first block from the list and return it. Yeah, so all of these are O of 1. So it makes it a lot easier rather than O of n, which we had for the linked list operator. Right? We had to walk the list to find a block. Here, each one of these operations is O of 1. Most notably, we can always return the first element of the list and no longer need to traverse the full list. Thus, allocations are much faster than with the list-linked allocator. Block sizes and wasted memory. Depending on the block sizes, we lose a lot of memory by rounding up. For example, when a 512-byte block is returned for a 128-byte allocation, 3/4 of the allocated memory are unused. By defining reasonable block sizes, it's possible to limit the amount of wasted memory to some degree. For example, when using powers of 2 as block sizes, we can limit memory waste to half the allocation size in the worst case and 1/4 of the allocation size in the average case. It's also common to optimize block sizes based on common allocation sizes in a program. For example, we could additionally add block size 24 to improve memory usage for programs that often perform allocations at 24 bytes. This way, the amount of wasted memory can often be reduced without losing the performance benefits. Deallocation. Like allocation, deallocation is also very performant. It involves the following steps. Round up the freed allocation size to the next block size. This is required since the compiler only passes the requested allocation size to dealloc, not the size of the block that was returned by alloc. By using the same size adjustment function in both alloc and dealloc, we can make sure that we always free the correct amount of memory. Retrieve the head pointer for the list, for example, from an array. Add the free block to the front of the list by updating the head pointer. Most notably, no traversal of the list is required for deallocation either. This means that the time required for a dealloc call stays the same regardless of list length. Right? Oh, they're all O of 1. Fallback allocator. Given that large allocations, greater than 2K, are often rare, especially in operating system kernels, it might make sense to fall back to a different allocator for these allocations. For example, we could fall back to a linked list allocator for allocations greater than 2048 bytes in order to reduce memory waste. Since only very few allocations of that size are expected, the linked list would stay small so that deallocations would still be reasonably fast. Creating new blocks. Above, we always assume that there are always enough blocks of specific size in the list to fulfill all allocation requests. However, at some point, the linked list for a block size becomes empty. At this point, there are two ways how we can create new unused blocks of a specific size to fulfill an allocation request. Allocate a new block from the fallback allocator, if there is one, or split a larger block from a different list. This best works if block sizes are powers of 2. For example, a 32-byte block can be split into two 16-byte blocks. For our implementation, we will allocate new blocks from the fallback allocator since the implementation is much simpler. Now that we know how a fixed size block allocator works, we can start our implementation. We won't depend on the implementation of the linked list allocator created in the previous section, so you can follow this part even if you skip the linked list allocator implementation. We'll start our implementation by creating a list node type in a new allocator fixed size block module. Okay, so let's get our hands dirty right away. So, oh, right, it's in the allocator module. No. So it's allocator.rs, right? So pub mod fixed size block. Right, and then this fails because we didn't create it. Fixed sized size block. Not without a D. Okay, struct list node. Next option. This is just like the other one, right? Static list node. Okay, so now it's building. Good. This type is similar to the list node type of our linked list allocator implementation, with the difference that we don't have a second size field. The size field isn't needed because every block in a list has the same size with a fixed size block allocator design. Block sizes. Next, we define a constant block sizes slice with the block sizes used for our implementation. Eight. We have to guarantee that this one is big enough to fit this. So kind of cheating here, I think, but 36, 34, 128, 256, 512. And 24 and 2048. Okay. As block sizes, we use powers of 2 starting from 8 up to 2048. We don't define any block sizes smaller than 8 because each block must be capable of storing a 64-bit pointer to the next block when freed. For allocations greater than 2048 bytes, we will fall back to a linked list allocator. To simplify the implementation, we define that the size of a block is also its required alignment in memory. So a 16-byte block is always aligned on a 16-byte boundary, and a 512-byte block is aligned on a 512-byte boundary. Since alignments always need to be powers of 2, this rules out any other block sizes. If we need block sizes that are not powers of 2 in the future, we can still adjust our implementation for this, e.g. by defining a second block alignments array. The allocator type. Using the list node type and the block sizes slice, we can now define our allocator type. Okay. List heads is in a slice of option static mute list node block sizes dot len fallback. This must be something we're pulling in. I didn't see it here as a use statement. Okay, but we'll see. Maybe we're going to use the crate instead. The list heads field is an array of head pointers, one for each block size. This is implemented by using the len of the block sizes slice as the array length. As a fallback allocator for allocations larger than the largest block size, we use the allocator provided by the linked list allocator. We could also use the linked list allocator we implemented ourselves instead, but it has the disadvantage that it does not merge freed blocks. All right. For constructing a fixed size block allocator, we provide the same new and init functions that we implemented for the other allocator types too. Okay, so we created an empty that's just equal to the value of none. Okay, and then list heads. I guess we had to do that for this. We couldn't put the word none in here, maybe? Because it's a static mute. I don't know, I'm just guessing. Maybe they'll talk about it. Fallback, allocator. Linked list, allocator, heap, empty. Okay, and then we're going to pub unsafe function init, self heap start, and heap size is a usize. We're just going to self fallback allocator init heap start heap size. In order for this to work, we're going to have to use the linked list allocator allocate the regions for these guys as well. So we're basically layering this on top of this thing. That's the way I'm reading it, but let's see where we go from here. The new function just initializes the list heads array with empty nodes and creates an empty linked list allocator as the fallback allocator. Right. The empty constant is needed because to tell the Rust compiler that we want to initialize the array with a constant value. This needs a grammar fix, I think. Initializing the array directly as none does not work because then the compiler requires the option static mute list node implements the copy trait, which it does not. This is a current limitation of the Rust compiler, which might go away in the future. All right, let's see. Typo here. Block sizes. Ooh, I missed the Z in here. And block sizes. Okay. All right. So actually, let's find out. Let's see if I can put a none here instead. No, it's still a limitation on the Rust compiler. If you haven't done so already for the linked list allocator implementation, you also need to add feature constant mute refs to the beginning of your lib.rs. We did that already. We did that in the previous video. The reason is that any use of mutable reference types in a const functions is still unstable, including option static mute list node array element type of the list heads field, even if we set it to none. And we can take a look at that real quick. It's this one here. All right, so this should build, and it does. The unsafe init function only calls the init function of the fallback allocator without doing any additional initialization of the list heads array. Instead, we will initialize the lists lazily on alloc and dealloc calls. All right. For convenience, we also create a private fallback alloc method that allocates using the fallback allocator. Okay, let's do that. Looks like we have to add a couple of things here. Use alloc layout, use core pointer. And then down here, we'll say fallback alloc, which is the layout, and returns a pointer to a byte, mutable pointer to a byte. Match self fallback allocator allocate first fit layout. If it's okay, if it worked, we return the pointer as a pointer. If it failed, then we're going to return pointer null mute. Return a null pointer on failure. And that failed because I forgot the R there. Okay, good. Since the heap type of the linked list allocator crate does not implement global alloc, as it's not possible without locking, maybe that's a comma there. Instead, it provides an allocate first fit method that has a slightly different interface. Instead of returning a star mute 8 and using a null pointer to signal an error, it returns a result non-null U8 unit. The non-null type is an abstraction for a raw pointer that is guaranteed to be not the null pointer. By mapping the OK case to the non-null as pointer method and the error case to a null pointer, we can easily translate this back to a star mute U8 type. Okay. Calculating the list index. Before we implement the global alloc trait, we define a list index helper function that returns the lowest possible block size for a given layout. Okay. List index takes a layout and returns an option U size. Let required block size, layout size, max, layout, align. Block sizes, iter, position, S is greater than or equal to required block size. Okay. So now we went, I mean, it's a short enough array, so it's effectively O of 1. I mean, in terms of, but it's still O of n search. I guess there's no better way to do it unless you guarantee you have every power of 2 between 8 and 2048. There's no way to know. And this also will work for any, this will also allow it to work for any sizes that we put in here. We could put oddball sizes in here and it'll still work. And I guess it doesn't even need to be sorted. It'll just find the first one that fits, right? But by sorting it, you guarantee you're going to have the one that's smallest will fit. All right, let's see what they say. The block must have at least the size and alignment required by the given layout. Since we define that the block size is also its alignment, this means that the required block size is the maximum of the layout's size and align attributes. To find the next larger block in the block sizes slice, we first use the iter method to get an iterator, and then the position method to find the index of the first block that is at least as large as the required block size. Note that we don't return the block size itself, but the index into the block sizes slice. The reason is that we want to use the returned index as an index into the list heads array. Implementing global alloc. The last step is to implement the global alloc trait. All right, let's do that up here. We do need super locked. And we don't need the align up that we implemented last time, I guess. And we need global alloc, and then down here we'll just impl global, oh, it's got to be unsafe, alloc for locked fixed size block allocator. And for now, we're just going to put to-dos in here. And dealloc as well, right? Okay. To-do. Okay. We got an error. Oh, because it's D. There. Okay, good. Like for other allocators, we don't implement the global alloc trait directly for our allocator type, but use the locked wrapper to add synchronized interior mutability. Since the alloc and dealloc implementations are relatively large, we introduce them one by one in the following. All right, we're starting with allocations. Relatively large? Well, it fits on one page, so that's good. The implementation of the alloc method looks like this. Okay, so we're going to start here. So we're going to lock the allocator. That makes sense. I'm going to leave a blank line there. List, index, layout. So this is going to this is calling this function we just wrote, list index, which is going to return an option usize, which is what position returns, right? So this could return a sum or a none. If we have a list index indicated by sum, node, list heads, index is equal to node next take, node as star mute, list node as star mute 8. Okay. How is this going to work though? Because we need to set the list head somewhere. Okay, and then if it's none, we could not find a block size that matched. So like if we tried to allocate 2049, that would return option none. Let block size is equal to block sizes index. Oh, I missed a level, didn't I? Yeah. Because this is this index. That's why I was getting lost there. So list index returns a sum. That means we're going to have something. And then we need to be able to take from there. Okay, so that's what I was missing. Okay, let's do this. Sum index. And then we say match allocator list heads index take. And this will take this thing here, right? So we have an index to a block size. It's just that, let's fix that. So if there is an entry in the head, if it's not none, then we can just grab it. If it is none, that means we haven't set up this block size yet. So let block align is block size. Let layout is layout. Oh, Lyndon, thank you for the follow. I must not have my audio set right because I didn't hear the... Oh, this is not good. I don't have my audio set up right. Oops, that's bad. Let layout equals layout from size align, block size and block align, unwrap, allocator, fallback, alloc layout. Right. So if we don't have an entry for this particular size, we're gonna go to the fallback alloc to allocate a block. Here, this says we haven't found a size, so we're gonna say we're gonna go to the fallback allocator. I don't see where we're actually initializing list heads though, so maybe that's coming in a little bit, because we do need something somewhere along the lines for that. Let's go through it step by step now. Okay, first we take the locked, right, method to get a mutable reference to the allocator. Next we call list index function we just defined to calculate the appropriate block size for a given layout and get the corresponding index to the list heads array. If this index is none, no block size fits for this allocation, therefore we use the fallback allocator using the fallback alloc function. If the list index is some, we try to remove the first node in the corresponding list started by the list heads of index using the option take method. If the list is not empty, we enter the some node branch of the match statement where we point the head pointer of the list to the successor of the popped node by using take again. Finally, we return the popped node pointer as a mute, U8. I forgot the U8. Like that. If the list head is none, it indicates that the list of blocks is empty. This means that we need to construct a new block as described above. For that, we first get the current block size from the block sizes slice. Right? So if we're trying to allocate 256, we're going to grab that size through the index. We're going to use the same block alignment as the block size. And use it for both the size and alignment for the new block. Then we create a new layout from it and call the fallback alloc method to perform the allocation. The reason for adjusting the layout and alignment is that the block will be added to the block list in deallocation. Oh, I see. So that's how we set the list heads. We don't initialize them here. See, I was thinking, well, okay, well, it's pre-alloc some and then hand them out. But no, we're going to do it on deallocation. Interesting. Okay. So the dealloc implementation looks like this. Well, let's see if this builds. It does not. What's missing here? List index. Did I typo that? No, there's list index. Oh, it's got to be self list index, right? Oh, maybe list index is a... Yeah, it's not a... Rather than having it a dangling function, why don't we just do it fancy, right? Fixed size block allocator, : Yeah. That way it's part of the thing, rather than just a dangling function. Although there's nothing wrong with just having functions. Local static functions. Okay, so let's look at dealloc. We're going to have to update our use statements here. We're going to have to include mem, pointer, and pointer non-null. Okay. So here's our dealloc. So we're going to do the same thing, lock the allocator. Fixed size block allocator : list index of layout, some index, let's see, next is going to be allocator list heads index take. Right? I think I got that right. Verify that block has size and alignment required for storing node. The only way that would happen, block sizes index, is if we didn't get our sizes right. Right? So if we tried to allocate 8 and this list node ended up being bigger than 8, then that's when that assert would blow. And we just have to say, okay, well, our minimum size is now, and I guess we can't get it at compile time. We can't get the size of list node for the minimum and then power of 2 it up or something. I don't know. Okay, so we did this. And let me put these separate so we can see them as separate from the rest of the code. New node pointer is pointer as list node. New node pointer dot write new node. Allocator list heads. Is write the unsafe thing here? Yeah, so this is the unsafe function, being able to write a value into a piece of memory. Yeah, inline always. Okay. List heads of index is equal to sum mute new node pointer. And then we're going to say none. So if we couldn't find an index for it, that means we must have gotten it from the fallback allocator. So we'll return it to the fallback allocator. And this fails because I forgot to do that. Okay, so let's read. Like in alloc, we first use the lock method to get a mutable allocator reference, and then the list index function to get the block list corresponding to a given layout. If the index is none, no fitting block size exists in block sizes, which indicates that the allocation was created by the fallback allocator. Right? Therefore, we use its deallocate to free the memory again. The method expects a non-null instead of a star mute U8, so we need to convert the pointer first. The unwrap call only fails when the pointer is null, which should never happen when the compiler calls dealloc. If list index returns a block index, we need to add the freed memory block to the list. For that, we first create a new list node that points to the current list head, whatever that is. This could be none, right? Or it could be pointing to an existing node. By using option take again, before we write the new node into the freed memory block, we first assert that the current block size specified by index has the required size and alignment for storing a list node. Then we perform the write by converting the given star mute 8 pointer to a star mute list node pointer, and then calling the unsafe write method on it. The last step is to set the head pointer of the list, which is currently none, since we called take on it, to our newly written list node. For that, we convert the raw new node pointer to a mutable reference. Yep. There are a few things worth noting. We don't differentiate between blocks allocated from a block list and blocks allocated from the fallback allocator. This means that new blocks created in alloc are added to the block list on dealloc, thereby increasing the number of blocks of that size. The alloc method is the only place where new blocks are created in our implementation. This means that we initially start with empty block lists and only fill the lists lazily when allocations for that block size are performed. We don't need unsafe blocks in alloc and dealloc, even though we perform some unsafe operations. The reason is that Rust currently treats the complete body of unsafe functions as one large unsafe blocks. Since using explicit unsafe blocks has the advantage that it's obvious which operations are unsafe and which not, there's a proposed RFC to change this behavior. Yeah, so we don't know, because we marked the whole thing unsafe, we could do anything unsafe in here, but it's probably better to make the unsafe operations more explicit, right? Using it. To use our new fixed size block allocator, we need to update the allocator static in the allocator module. Okay. So that's just this guy here. So we have to say use fixed size block. And then we can just put that here. We can put that here. Since the init function behaves the same for all allocators we implemented, we don't need to modify the init call in init heap. Yeah, because we're just implementing a frame allocator. Okay. Here it is. Allocator lock init heap start heap size. When we now run our heap allocation tests again, all tests should still pass. Let's save that. Oh, we have a couple of warnings. Oh, because we're not using that. Huh. Why isn't it complaining about the Oh, I was going to ask why it wasn't complaining about the bump allocator, but that's because we removed it. We still use it, pub mod it here, but we don't use it. Okay. So now I should be able to say cargo test heap allocation. Yeah, and it all works. Our new allocator seems to work. Discussion. While the fixed size block approach has a much better performance than linked list approach, it wastes up to half the memory when using powers of 2 as block sizes. Whether this trade-off is worth it heavily depends on the application type. For an operating system kernel where performance is critical, the fixed size block approach seems to be the better choice. On the implementation side, there are various things that we could improve in our current implementation. Instead of only allocating blocks lazily using a fallback allocator, it might be better to pre-fill the lists to improve the performance of initial allocations. To simplify the implementation, we only allowed block sizes that are powers of 2 so that we could use them also as the block alignment. By storing or calculating the alignment a different way, we could also allow arbitrary other block sizes. This way we could add more block sizes, for example, for common allocation sizes in order to minimize the wasted memory. We currently only create new blocks but never free them again. This results in fragmentation and might eventually result in allocation failure for large allocations. It might make sense to enforce a maximum list length for each block size. When the maximum length is reached, subsequent deallocations are freed using the fallback allocator instead of being added to the list. Instead of falling back to a linked list allocator, we could have a special allocator for allocations greater than 4K. The idea is to utilize paging, which operates on 4K pages, to map a continuous block of virtual memory to a non-continuous physical frames. This way, fragmentation of unused memory is no longer a problem for large allocations. With such a page allocator, it might make sense to add block sizes up to 4K and drop the linked list allocator completely. The main advantages of this would be reduced fragmentation and improved performance predictability, i.e. better worst-case performance. It's important to note that the implementation improvements outlined above are only suggestions. Allocators used in operating system kernels are typically highly optimized to specific workload of the kernel, which is only possible through extensive profiling. All right, so we have something that works, right? We can say git add source, git commit, fixed size block allocator. All right, variations. There are also many variations of the fixed size block allocator design. Two popular examples are the slab allocator and the buddy allocator, which are also used in popular kernels such as Linux. In the following, we give a short introduction to these two designs. The idea behind a slab allocator is to use block sizes that directly correspond to selected types in the kernel. This way, allocations of those types fit a block size exactly and no memory is wasted. Sometimes it might even be possible to pre-initialize type instances in unused blocks to further improve performance. Slab allocation is often combined with other allocators. For example, it could be used together with fixed size block allocator to further split an allocated block in order to reduce memory waste. It's also often used to implement an object pool pattern on top of single large allocation. Buddy allocator. Instead of using a linked list to manage freed blocks, the buddy allocator design uses binary tree data structure together with the power of 2 block sizes. When a new block of a certain size is required, it splits a larger size block into 2 halves, thereby creating 2 child nodes in a tree. Whenever a block is freed again, the neighbor block in the tree is analyzed. If the neighbor is also free, the 2 blocks are joined back together to a block of twice the size. The advantage of this merge process is that external fragmentation is reduced so that small freed blocks can be reused for a large allocation. It also does not use a fallback allocator, so the performance is more predictable. The biggest drawback is that only power of 2 block sizes are possible, which might result in a large amount of wasted memory due to internal fragmentation. For this reason, buddy allocators are often combined with a slab allocator to further split an allocated block into multiple smaller blocks. Summary. This post gave an overview over different allocator designs. We learned how to implement a basic bump allocator, which hands out memory linearly by increasing a single next pointer. While bump allocation is very fast, it can only reuse memory after all allocations have been freed. For this reason, it's rarely used as a global allocator. Next, we created a linked list allocator that uses the freed memory blocks itself to create a linked list, the so-called free list. This list makes it possible to store an arbitrary number of freed blocks of different sizes. While no memory waste occurs, the approach suffers from poor performance because an allocation request might require a complete traversal of the list. Our implementation also suffers from external fragmentation because it does not merge adjacent freed blocks back together. To fix performance problems of the linked list approach, we created a fixed size block allocator that predefines a fixed set of block sizes. For each block size, a separate free list exists so that allocations and deallocations only need to insert/pop at the front of the list and are thus very fast. Since each allocation is rounded up to the next larger block size, some memory is wasted due to internal fragmentation. There are many more allocator designs with different trade-offs. Slab allocation works well. Sorry, I lost my place there. Slab allocation works well to optimize the allocation of common fixed-size structures, but is not applicable in all situations. Bunny allocations uses binary tree to merge freed blocks back together, but wastes a large amount of memory because it only supports power of 2 block sizes. It's also important to remember that each kernel implementation has a unique workload, so there's no best allocator design that fits all cases. Okay, that, my friends, is the end of the allocator design section.